So in terms of our agenda updates, we're going to have Todd Topersky up next. He's going to be covering coupling mechanisms in your radiated emissions setup. And then after, Todd's going to do 2 presentations in a row. So between his presentations, we'll take like a 5 or 10 minute break. And then we'll have our final session at the end of the day with Mark Malik where to wrap up the day. So it looks like we've got Todd queued up and ready to go. So Todd, I will turn it over to you.
Okay, Kelly, can you hear me okay?
If I unmute you, then I can tell you that yes, I hear you loud and clear and your slides look great. So you are good to go.
Okay, thank you. Okay, just let me, oops. Go to the laser pointer. Okay. Well, good morning, everyone. Thank you for joining our EMC webinars this week. My name is Todd Topersky. I'm a principal FAE for MPS located in the Detroit area here in Michigan. I have a little over 25 years of designing and supporting EMC compliant systems and board designs, whether it was products that I worked on previously in my career or supporting customers for about the last 18 years. I've had a lot of exposure to EMC and EMI problems and helping customers overcome that. I've been at MPS for a little over 2 years. I had the experience of starting at a new company 2 weeks before the COVID pandemic hit. So that was definitely an interesting time for several months, but it's been going well. And my role here is to support automotive customers with our different power designs. And a big part of that is related to EMC testing, debugging, support. I also work very closely with our product teams to help define new automotive power and lighting solutions. Prior to that, I was an FAE at TI for about 16 years, also supporting automotive customers. And then in the first, 12 years or so of my career, I worked as a hardware and system design engineer, working on a variety of different products. At one company, I was working on automotive audio and infotainment systems. I also spent time working on consumer electronics, several years working in industrial power and motor starters. So spent a lot of exposure to different types of noise problems. And then for my background in education, I completed my graduate degree at Georgia Tech, and before that, my undergrad at Michigan Tech. So for today's topic, today's session will be looking at several different things. The first is we're going to dig into the definition of radiated emissions, what that means, what we perceive it to mean, and what it may actually be, depending on what your test setup is. Then we'll get into looking at several of the common radiated emission setups, including FCC and CISPR 25, and try to think of it perhaps in a way that maybe some of us have not in the past, in terms of what we're measuring and what we might be able to do in terms of coming up with a plan to solve our problems. Then we'll get into unintentional coupling paths in our DUT setup. Then we'll get into some tips and considerations for when we're measuring radiated emissions, and then we'll summarize at the end. So before we get into our material, I'd like to throw out a pop quiz to everybody, just to kind of get us thinking along these lines early in the session. So here we have a setup where we have a power supply board on the right here. It's DC to DC converter, a buck converter that steps from 12 volts down to 5 volts. It's providing about 2 amps and it switches at 2 megahertz. We have a 2-meter long cable connected to these 2 lizens, which are powered by a car battery. As we can see here, this device under test, or DUT, as I'll call it throughout most of the presentation, this is unshielded, so it's nothing metal surrounding it. And our antenna here is a monopole antenna, which is about 1 meter distance from the cabling here on this table. So when we do our measurement, we come up with a spectrum shown here from 150 kilohertz out to about 30 megahertz, where we can see noise spurs. Obviously, we have a 2 megahertz noise spur and then a bunch of other ones that follow it. And when we take a closer look at the results, we see at 6 megahertz here, we actually have a failure. We're about a dB or so above the limit. So when we take this kind of measurement and look at this data, what can we assess about what could be our largest contributor of noise? So the question is, what is likely the largest contributor of noise measured in the spectrum? Is it A, electromagnetic waves emitting from our device or from the buck converter? B, electric fields coupling from the buck converter? C, electromagnetic waves emitting from a 2-meter cable harness? Or D, none of the above? So if you have an answer, you might jot it down in your notes or just think about that more, but we'll come back to this later. So defining radiated emissions, excuse me, radiated emissions or radiated coupling occurs when we have electromagnetic energy comprised of both an E field and H field being emitted from a source, such as a mobile handheld device shown here. The resulting electromagnetic wave propagates to the far field to a device that may not be located very close. And in this far field, there could be a victim circuit in which voltages and currents are induced and could create noise problems. When we think about what true radiated emissions is, we're really describing or talking about an electromagnetic wave, as shown here. And this is, something that I'm sure many of us have seen in previous coursework related to electromagnetic theory, et cetera, or physics, physics classes. We have an electromagnetic wave with a couple of components here propagating in a direction. The key properties that we want to review related to these waves are that they're a plane wave, meaning that they're propagating in a certain direction along a certain path. As shown here, this wave is propagating along this axis, which is kind of like in the X direction. An electromagnetic wave is comprised of 2 components, one being an electric field, the other being a magnetic field, which are always at right angles to each other, so they're always perpendicular. The speed of an electromagnetic wave is the speed of light. So in a vacuum, we're talking about 300 million meters per second. These waves, when propagating in the far field, will always have a wave impedance that is equal to about 377 ohms. And this wave impedance can always be calculated if we know either component, like the electric field or the H field. We can use that to calculate what the other field is. And this is important as we learn how to deal with EMI and trying to separate sources from victims. It's important to understand that Both of these fields in an electromagnetic wave will attenuate at a rate of 1 over distance as the distance increases. Now, as we think about the far field, and as we try to understand like what the sources of noise creating that far field electromagnetic wave are, we get closer to the source. And as we get closer to the source of the noise, we can start to separate out the components a little bit better and try to understand them, because as we get into the near field, the electric fields and magnetic fields will exhibit different properties than they will as a far field electromagnetic wave. So here we take a closer look at electric field coupling. And for electric field coupling to occur, we typically have a source, as shown here on the left, that is switching a voltage or driving a time varying voltage that has a very large dV/dt characteristic. So this is changing very quickly. It could have sharp edges over a short period of time. For coupling to occur, we need to have a victim circuit, and that circuit for an electric field will typically be something that has higher impedance. So we could be looking at a circuit that has a high input impedance or a high load impedance or some combination of both. And the distance here is critical. As you know, the closer we get, the more likely that there could be coupling between this high dV/dt and this high impedance victim source. One thing that's important to understand about electric fields in the near field is that they attenuate much faster than an electromagnetic wave as the distance increases. So as we can see here, in the near field, an electric field can attenuate at either 1 over distance cube or 1 over distance square, depending on the conditions. And we'll touch on those conditions in a couple of slides and to help it make a little more sense. The other component, which is a magnetic field, can also couple in the near field, and it is usually driven by a current source or a high dI/dt source. Oops, I apologize. So with a high dI/dt source, we can generate a very sharp change in current that can travel around the circuit, which is typically a lower impedance circuit. You can have some higher load impedance, but the source impedance typically tends to be lower for a high dI/dt circuit. And as we have these circuits drawn here, we're showing 2 inductances, one on the source circuit side, one on the victim circuit side. These can be inductances that are formed either from the circuit itself, from traces or, parasitics in the connections, or it could actually be inductive components. So either way you look at it, this can be a problem as long as there's some type of inductance involved. It's most commonly a problem near a victim circuit which has a higher impedance for the load or has a large loop area. So if you have either one of those characteristics, you're more susceptible to a nearby high dI/dt problem. And like an electric field, magnetic fields in the near field will attenuate much faster than an electromagnetic wave. So as we increase the distance away from the source of noise, an H field will attenuate at a rate of 1 over d squared or 1 over d cubed, depending on the conditions. Now, as we get into talking more about near field and far field, we'd like to understand better how do we define where this boundary is, especially for our EMC measurements. Where can we make use of this knowledge and try to understand where the near field ends, where the far field begins. And unfortunately, this is kind of a controversial topic among RF and EMC engineers. If you ask a guy who designs antennas or sensitive RF circuits where the far field begins, you're likely to get a much different answer than you would from an EMC engineer who's trying to debug noise measurements that are coming off of a product. In general, an RF engineer will define multiple transition regions between the near field and far field. And this is typically based on wave impedance regions. So some RF engineers may say the far field begins at one wavelength from the source of noise. Others may say it starts at 2 wavelengths. It depends on, I think, the information that they were taught and the textbooks, the papers that are written, and the details that are out there in the industry based on all the different types of antennas and how they're designed and their different wave impedance characteristics. Fortunately, when we're dealing with EMC problems, we tend to simplify this approach a little bit, and we try to use a 2-region approach. With this kind of model, we're defining the far field as the beginning of where E and H are approaching a radiative behavior, which means they're becoming more like a plane wave in the far field. So if we keep that in mind, we can define the near field reactive component as the field that's within a distance of lambda over 2 pi, or it's approximately lambda over 6. And then anything beyond that point, we can consider it to be a radiative type of plane wave, and we consider that the far field. So a diagram that shows this perhaps a little more clearly is this diagram where we show a source of emissions in the center here, and the near field reactive portion of or field is located here from the source out to a distance of about lambda over 2 pi. And you can see this is all in surrounding the source. It's, this near field can be emitting in all directions. And so we need to consider this in our test setup in our measurements. Once we get beyond this distance of lambda over 2 pi, we're then mostly talking about a far field radiative type of phenomena where we're dealing more with a plane wave. So for the rest of these slides and the rest of my material, we'll be using this 2-region approach for our discussion. Okay, so in this slide, we show a wave impedance curve, which is showing wave impedance versus distance from a noise source. And this is a very interesting tool, in my opinion, to use because it kind of helps us understand beyond the transition point what's going on between these fields on either side of this transition point here. So this is normalized to lambda over 2 pi. So at 1 here, this is our lambda over 2 pi where our far field transition begins. What we'll notice here, and I think a useful way to think about this is if you start in the far field and you work your way back towards the noise source, you'll see that if we're able to actually measure the wave impedance as we get closer to the source, you'll see that if it starts becoming a higher impedance, we're probably talking about something that is a strong E field. On the other hand, if we're approaching our noise source and we see that the wave impedance is starting to reduce or get much smaller, then we can assume that what we're dealing with is predominantly an H field. And in this diagram, what we show here is that the source in this curve is actually a dipole antenna. So it's an electric field antenna being used as the source of noise generation. And on the bottom here, we're talking about a loop antenna or magnetic field antenna that's generating an H field. In both cases, there's an H field component for a strong E field situation. And in the situation where you have a predominant H field, there will also be an E field involved, but it'll be smaller. So just remember that wherever there's an H field, there's certain to be an E field, because there's always a voltage and current association. In the same thing, where there's a strong E field, there should also be a magnetic field or H field, but it will be much smaller compared to the dominant E field. So as we get closer to the noise source, and if the source is an E field, we will see this higher impedance. And here we can understand that capacitive coupling will be the dominant factor. And this will be, the likely type of coupling that we see on our printed circuit board or in our circuit. As we get closer to the dipole antenna here, or to any noise source that could be on our circuit boards, we'll see that the electric field will vary as 1 over distance cubed. So it's proportional to 1 over distance cubed as distance increases. The H field will vary as 1 over distance squared. And then the wave impedance will vary as 1 over the distance, which is basically this curve, sort of a linear curve here for the E field as it decreases. As we get closer to the source of noise for a magnetic field, and the impedance decreases, we see that this curve has a characteristic of changing proportionally to 1 over d cubed, much like the E field does. The E field component, even though it's smaller here, will vary as 1 over d square, and our wave impedance will vary as distance increases. And then, of course, as we get out past the boundary here and into the far field, we then take on the electromagnetic field properties that we previously discussed, where both E and H will decrease as 1 over the distance, and our wave impedance will stay constant at about 377 ohms. This is a table that I put together just more as a reference point for looking at near field boundaries associated with some common frequencies that we may use in our designs for like switching regulators, buck converters, boost converters. To calculate this, it's very straightforward. We take our basic equation of lambda equals the speed of light divided by the frequency, and we determine what our lambda is, and then we divide that by 2 pi, which is approximately equal to lambda over 6. And here is our estimate for the near field boundary. We can see here for like 100 kilohertz, we're at the near field boundary is very far away. We're talking like over a quarter mile away from the noise source. As we get up to a frequency of 1 or 2 megahertz, now we're in the tens of meters. So at 2 megahertz, we're talking about 25 meter near field boundary, which is still quite a long distance. It's when we get up into the higher frequencies where this near field boundary gets pulled in closer and closer to the source, and then our problem becomes more far field. Okay, so in this next section, we'll take a closer look at radiated emissions setups based on, trying to look at it from a perspective of wavelength in far field and near field. So here we show a typical setup for FCC radiated emissions for Part 15 Class B. As noted here, this is actually a photograph of the chamber located in our Livonia, Michigan EMC lab. This is our 3 meter chamber. So as the diagram shows here, we have our device under test sitting on this rotating table. This bilog antenna is placed about 3 meters from the device that's being tested. And this antenna is capable of measuring over a wide range from 30 megahertz to 1 gigahertz. So if we look at the lower bound of this range, which is 30 megahertz, we can calculate that we have a near field boundary of about 1.6 or 1.67 meters. We measure that from the distance from our device that we're testing. We'll see that that's a little bit over halfway to the distance of the antenna. So here we can clearly see that the far field will be beyond this point, and near field is on this other side closer to the dot. And what we can deduce from this is that for all of these measurements, 30 megahertz and higher, we will definitely be dealing with far field measurements. So everything that we measure will be a propagating electromagnetic wave coming off of our setup here. Now, as we get into CISPR 25, things could get a little different. There's a little more variety here with the different antennas that are used. At the low frequency range, we use a monopole or rod antenna, which is optimized for measuring from 150 kilohertz up to 30 megahertz. In the middle photograph here, we show a biconical, or what we call bicon antenna, which is optimized for 30 megahertz to 300 megahertz. And then finally on the right side, we use a log periodic antenna, which we often just call log antenna, to measure the higher frequency range, which goes from 300 megahertz up to 1 gigahertz. All of these setups are common and have common properties except for the antenna. We'll see that the device under test and wire harness are always placed on 50 millimeters of insulation on this copper table. The wire harness is always 2 meters long. For automotive applications, these modules will always be powered by a 12-volt battery that's connected to a pair of lizards. This conductive table will always be connected to ground, and the antenna will always be positioned 1 meter from the wire harness here and centered halfway between the ends of the wire harness. So here we're going to look a little bit closely, or more closely, at the monopole antenna setup. So here's our rod antenna. It's approximately 1 meter from our device under test. What we notice, is that 1 meter compared to 3 meters is fairly close. So this is definitely probably a little tougher setup than an FCC test, which most of us already know that's the case. The interesting thing though is we measure at a lower frequency in this setup than we would for FCC. So we're measuring from 150 kilohertz to 30 megahertz, 1 meter from the device. And when we look at what the near field boundaries are for these ranges of frequencies, if we look at 150 kilohertz, we're talking about a near field that's close to a quarter mile away. And for the high end, which is 30 megahertz, we're talking about near field being about 1.6 to 1.7 meters away. Well, if we look at that distance here, we see that this near field boundary actually goes beyond where the monopole antenna is. And so, a lot of us who are starting out doing emissions testing or trying to understand how to mitigate these problems and how to debug them may not realize that what we're actually dealing with here is not far field emissions. These are not electromagnetic waves we're measuring at this point. What we're really measuring is near field. And when we're this close to the device under test with this frequency range, we're most likely measuring E-field coupling or capacitive coupling that's coming off our setup. Okay, so as we go up to the next couple sets of antennas, which would be Bicon being used for 30 megahertz to 200 megahertz, and then log for the higher range up to 1 gigahertz, we still have the same distance here. It's 1 meter, but we have some differences in the frequencies. So if we look at the low range of 30 megahertz, what we'll see is, as we calculated before, that we're at about 1.6 to 1.7 meters. So at the start of this Bicon range, we're still very likely in the near field with what our measurements are showing us. And then as we start to increase frequency, at what point do we actually start becoming far field? And if you calculate it here for 50 megahertz, you'll see that that's approximately the near field boundary for 50 megahertz is at about 1 meter. So it's right at about the distance where the antenna is. So what we can come away with from this is that, in the very low frequency range of Bicon measurements, we're mostly dealing with a near field problem. And as we get up to about 50 megahertz and beyond, now we're dealing with a radiated problem that's really more of an electromagnetic wave propagating. So, these are the kind of things that are important for us to consider as we go about trying to debug these problems. Okay, so in the next section, we'll take a look at unintentional coupling paths in our DUT setup. Here, we'll give a little background on dipole antennas. So a dipole antenna is a very simple antenna structure that is typically used for either generating or measuring E-field. And as shown here, it typically has 2 legs or 2 poles. So we have an upper leg here, which is about 1/4 of a wavelength long. And the bottom leg is also 1/4 of a wavelength long. So if we were to sum these 2 legs together, we would come up with half of a wavelength, which is why we come up with the name half-wave dipole. So here we just show a couple of calculations where we can take the length and convert it into a lambda. Basically our lambda would be equal to 2 times L in this case for the antenna, and then we can plug that into our equation for frequency and speed of light, and we can come up with the frequency at which this type of antenna will most efficiently radiate. And this isn't to say that it can only radiate efficiently at that frequency. It can also radiate at other frequencies that have similar characteristics to that wavelength. For example, it could be a 1/4 wavelength could become a problem, an 1/8 or a 1/10 of a wavelength. These things can radiate sometimes effectively out to like a lambda over 20. So it's just a little bit of understanding of how efficient these can help us in understanding our EMC problems. We also want to take a look at a special case of a dipole, which is a 1/4 wave monopole. And basically a 1/4 wave monopole is very much like a dipole, except that we're replacing the bottom leg with a reference plane, which, this could be a ground plane. This could be like the copper plane on our test table when we do EMC testing. What we see here is that now we're only dealing really with the upper leg, which has a length of a 1/4 wavelength. And similar to what we did for the half-wave dipole, we can plug this into our equation and calculate the frequency at which it will most effectively radiate, but it is also capable of radiating frequencies higher than this frequency. So in our setup, for our CISPR-25 setup especially, we almost always deal with longer cables, cables that might be 1.7 meters out to 2 meters. And we need to consider that these long wires and anything that's a long conducting object can act as an unintentional antenna in our setup. And it can form an unintentional monopole or dipole, which we'll show in a moment. But basically, for wires that are this long in the 1.5 to 2 meter range, these are very capable of radiating noise in the range of 200 megahertz up to 300 megahertz. If the length changes, this range will change, but for our standard CISPR-25 setup, this is very common to see cables that could create problems up into this frequency range. And then as stated earlier, a large metal surface like our table, the copper surface under our board, under our setup, can also act as part of the antenna. It only takes a little bit of current that's coupling parasitically through an E field, between the DUTs or the printed circuit board to the table, or the cabling to the table to create some problems for us. And what's very common in these setups is that we are dealing with common mode currents, which are basically parasitic currents created that can be very small. Basically, if this is a power feed coming from a battery, our intended differential mode current here may be 1 amp, 2 amps, or something on the order of amps being pulled into the board and then returning back to the battery source on this leg. But the common mode currents are not as effective at canceling each other out like a differential mode current. So these are typically common to some other reference point in the system, and they are not effective at canceling each other out, so they circulate and they can create an emissions problem with our cables. These currents can be very small. We're talking nanoamps to microamp range, and they're created through a few different mechanisms. One of them, which is parasitic coupling or fields created in our PCB layout with currents circulated on the board, or coupling between traces in the power plane or ground plane. The ground plane is usually a very big problem for common mode emissions. It can also be parasitic coupling between the board and a metal surface, whether it's a table or an enclosure. And then the same thing with the cabling. The cabling can also couple between an enclosure or a copper table surface, and also form a path for these currents to return back to the board where they originate and then circulate through the cabling, creating radiated emissions problems. In the circuit boards, as we are dealing with the lower frequencies, like a couple hundred megahertz or less, typically we're not seeing too many problems with noise radiating off the boards or circuits on the boards. But as frequency increases and we get above 200 megahertz, the wavelengths continue to get smaller as frequency increases. Now the size of these different components on our board and the traces in circuit loops, circuit sizes start to really matter. So the things that we need to look out for once we start getting up into this frequency range are components that are relatively large on the printed circuit board. Like we could have a tall capacitor, like an aluminum electrolytic, which has a metal casing, or we could have a large inductor, which has a lot of copper wound inside of it, or aluminum or copper wiring. And then it also has terminals on the side, which could be capacitively coupling to the circuit board. If we have a circuit that's using a heat sink, especially larger heat sinks, coupled to a noisy IC, trying to provide thermal relief, we're also creating an unintentional antenna at certain frequencies. We need to be careful of that. And then it's not just electric field or parasitic capacitive coupling. We also have H field coupling, which we need to be aware of too. So, larger inductors will create larger magnetic fields that we have to deal with. And then also decoupling capacitors, which are used to help provide some filtering as well as some initial fast current supply for a fast switching edge. These are also loops that can create small magnetic fields underneath our ICs or near the ICs that they're decoupling. Also, the other thing we need to be aware of and pay close attention to are any of the current loops on our board, especially when we're dealing with power, motor drivers, buck controllers, any type of FET drivers. A lot of these applications will use external switches such as power FETs, and we'll have these small current loops which connect as a type of small magnetic dipole and then create a magnetic field that radiates from the board. So these are just other things we need to be careful of, especially at higher frequencies. One thing to remember is in the far field, what we're measuring, maybe E fields for the different antennas that we're using, but these E fields are one component of an electromagnetic wave, and that electromagnetic wave can actually be formed by an H field, not just an E field on the board. Okay, so to kind of summarize the last couple slides, in our setup, we need to pay close attention to large conductors such as cabling. These can act as unintentional dipoles. If we have some wire-to-wire interaction, that is a type of dipole. A case where the dipole can become really bad is if you have other cabling that comes off other sides of the board or opposite sides of the board. That can act as an even worse dipole antenna. Wherever we have a copper plane here, the surface being 50 millimeters underneath this wiring can still be enough to allow for electric field coupling, and we can create a type of monopole structure here in our setup. And we need to remember that these wires that are close to 2 meters long are very effective at radiating up to 200 megahertz, sometimes close to 300 megahertz. When we get up to higher frequencies, our DC-to-DC converter board or our DUT becomes more critical. So we need to pay attention to frequencies up in this range that can go from 200 megahertz and up to approaching a gigahertz. Because as we stated, these circuits and the components on the board become much more critical as these wavelengths get smaller and frequencies go up. And last but not least, the load is very critical. This can be something that can screw up your measurements if you're not careful. You want to make sure that wire connections are short. You want to make sure that you're not creating large loops that act as a magnetic dipole. So always make sure your load connections are very short and tightly coupled to your device that you're testing. Okay, so now we get into the last section, which is tips and considerations for when we're measuring radiated emissions. So based on our review so far, looking at a CISPR 25 setup where we have our DUT board here on the right side, 2 meters of cable running over to our LISMs. We have approximately 1 meter distance from the setup to our antenna, and then the distance to our DUT is a little more than that. It's about 1.5 meters. Based on the antenna that we're using, there are some some estimates and some preliminary decisions that we can make, based on what we're seeing, what we're using and measuring. So we know now that in this frequency range of 150 kilohertz to 30 megahertz, we're going to be dealing with mostly E field, which is near field coupling, as shown here with the capacitive coupling in our setup. And the coupling source that's likely the cause for this could be either one of these things. It could be the device under test, or it could be our cabling. And that's something that we'll need to determine. Then as we go up in frequency to a bicon antenna, we will see that we have a little bit of E field near the bottom part of this range, or near field measurements. So this could be E field coupling. But then as we increase in frequency at about 50 megahertz or above, we get more into true radiated emissions. So when we're at the bottom end of this range, the cables in the duct could both be critical sources for coupling noise. As we get into the higher frequencies and the problem becomes more far field, now we're going to be talking about the cables becoming very efficient radiators in this range. And then as we get up closer to 200 megahertz, we might start seeing problems related to the PCB, but there will be a transition point where the cabling and the PCB, one will be more dominant than the other. And it's up to you to determine that in your testing. Once we get to the highest frequency range for log antenna, now we're pretty much dealing with an electromagnetic wave that's propagating. This is far field radiation. And in this range, most of the problems we deal with are on the printed circuit board. Okay. So now back to our quiz. Based on everything that we've reviewed so far, I think it should be pretty apparent by now that in this setup for CISPR 25, using a rod monopole antenna, it should be pretty apparent that what we're dealing with here are not electromagnetic waves. So this is not a far field issue that we're measuring. We're measuring something that's close to the source of noise. It's most likely an electric field. So how do we deal with determining if B or D is the answer? How do we know if this is coming directly from our DUT, or could it be coming from the DUT and the cabling, or mostly from the cabling? So we'll take a quick look at that. In our original measurement, here is our spectrum. There's no shielding used of any sort in this measurement. To take a look at the contribution from the cabling, we can do a couple experiments. One is to shield the cable. And here we can either put the cabling between a couple pieces of cardboard or a couple pieces of wood and wrap it in some type of foil or mesh that's aluminum or copper, and then try to fasten this or tape it to the copper table. So in this setup, we do just that using aluminum foil. And what we see is that we get a little bit of improvement here, roughly about 3 to 5 dB reduction at most of the frequencies. So it's some improvement, but what we're looking for is something that is like a huge change in what we're measuring. So next we remove the foil and we put the DUT in a box that is shielded, and then we cover the input or the entrance part of the box with foil to try to cover this as much as possible while allowing our cabling to protrude from the front. And we'll notice now we have this significant change. We have a very large reduction in noise. In fact, what we're measuring here is 10 to 15 dB at most frequencies. So from this, we can come up with a pretty good guess as to what our dominant noise source is between these two things. So based on these results, we can see that B is the correct answer. The DUT is the largest noise contributor in the near field for this particular setup and measurement. Is this always the case? Will the DUT always be the problem, the larger problem for this setup? No, it not always. I mean, it depends on the circuit, the type of module that you're using, what the layout is. If you're using shielding over the module or partial shielding, all these things can play into how dominant the noise is coming from the DUT versus the cabling. But I think the key point made here is that we should not always assume that the cables are the primary issue when we measure these noise problems, and especially for the monopole setup for CISPR 25 based on the frequency range that we're dealing with. Why does this matter? It may change your approach to mitigating the problem in this frequency range. In the near field, a significant E field can couple directly from the antenna or to the antenna from the DUT or cable or from both. If we assumed the cable was the main problem, we may have spent a lot of time and perhaps money, because CISPR chambers are not cheap to do debugging. We may have spent a lot of time and money trying to work on filtering the cable or coming up with something related to the cable, when in this case, it likely would have shown a very small improvement. So what we've determined in this particular case is that the DUT is a larger noise problem at these frequencies, and we should focus on now trying to find the culprit on the printed circuit board. It could be a layout issue, it could be a noisy component, or some other problem. So in summary, in this session, we discussed many things, including far field radiated coupling from electromagnetic waves, near field coupling from E and H fields, how to estimate the boundary between near and far fields, understanding our radiated emission setup, and determining coupling mechanism based on the antenna type, the distance from the source, and near and far field boundary. We also looked at unintentional coupling paths in our DUT setup, and we reviewed some tips and considerations for measuring and debugging radiated emissions. So thank you for your time, and we can open it up to questions at this time.
Thanks a lot, Todd. Lots of good information in there today. Todd is doing the next session as well. Let's take one question here, then let's hold questions. We'll take a 5-minute break, and then Todd can answer any of the remaining questions following his second session. I want to make sure that we stay on schedule and get you guys all out.
I apologize, Kelly. I just realized I went over by a little bit.
No worries, but let's do the first question real quick. It's in the CISPR 25 setup, it seems like it would be important and beneficial to tightly twist the power feed cables going between the DUT and the LISN and the power source, or use coax cable. Is this allowed when doing this sort of test? It looks like a big source of variability.
Yeah, so that's a very good comment, and it's really dependent on the customer and what their setup is. So a lot of OEM customers cannot twist their cabling for their wire harness. Like their wire harness that they use in production may not be twisted. It may just be a bunch of strands of wire, running side by side. In other cases, it actually may be twisted pair. For example, like audio amplifiers, which are driving speakers, quite often use twisted pair wire. In some cases, yes, it could be coax, like for certain camera systems that are using coax. The answer is it depends on the application for the particular module that's being tested. That will determine the type of cabling that's used. They will use what they plan to use in production, and that may be twisted pair, it may be a coax, it may be unshielded, untwisted cabling. So it really just comes down to the customer and their application and what their requirements are.
Great. Okay, so I'm gonna hold the rest of the questions here. Let's take a 5-minute break, and we will be back at so 9:50 Pacific. So what's that make us? 12:50 Eastern, and then we'll start up with Todd's second session.
Thank you.